I will start the presentation. So thank you for the kind introduction. The main thing that I want to talk about is that for starters, I think that everybody would agree that these days we're pretty good in terms of scene description. So what I mean by scene description is essentially you feed an image into a network and then you get some kind of like um, purely descriptive output, which is simply a segmentation mask, for example, as we can see here with Sum3. Or in that case in 3D as well. These days there is like depth anything 3, which provide you with the entire, like, let's say, slam output and all of those other depth information. Um, but the thing is that this is purely descriptive, and one thing that we would try to reach with AGI, if you believe in AGI, and even if you don't believe, one natural extension of AI should mostly be to be able to perform scene understanding. So here I give you a brief example of what I mean by this. For example, if we feed an image and this prompt, which is which of the runner finished first, into a vision language model. So you guys might know LLaVA. It's just so you can chat with it and it understand images. Essentially, if you feed that very simple question that humans can easily answer, right? I mean, it's obvious that this person on the left, which is crossing the finish line, is definitely the first person, right? The winner of the race. But LLaVA really does not understand this, and the question is not about description anymore. It's about scene understanding, because here you have to make a link between the fact that the person who crosses the finish line first is the winner, right? Um, so it's deeper than simply describing the scene, right? Um, but one thing that we found was that actually using those kind of scene description, um, hints can help the model for scene understanding as well. So here so on the left, this is the exact same image as I showed earlier. But on the right now, you can see the only difference that we do is we simply create a depth graph. So this depth graph essentially encapsulates all of the geometrical information related to the depth of the image. So here, as you can see, we have 3% in that image, and they're represented as nodes in the graph. And each arrow represents the depth order between this element and another element. So for example, here, person 1, which would be this person on the left, there's an arrow going to person 2, which would be this person, and an arrow going to person 3, which is this person. So this arrow means person 1 is in front of person 2, and person 1 is in front of person 3. Now the same goes for person 2, which is in front of person 3. And when you build this kind of representations and you feed that into the model, so the way we specifically feed that into the model is because this model understands bounding boxes. So we just get the bounding box for person 1, and we convert this graph as a textual graph. So we're saying essentially the person 1 at location X, right, is in front of person 2 at location X. So we're converting this into a textual format, and we're sending this into the vision language model. And now you can see that based on this simple geometrical rounding, in a fully zero-shot manner, because this model is frozen at all time, we can now understand the scene better. And most of my talk is going to be revolving around this. Like, how do we create those kind of graphs that can be able to not only describe the scene, but can be used to also understand the scene? So, what kind of understanding specifically? Well, that's a good question. And in this talk, we're mostly going to focus, and we're only going to focus on depth and occlusion understanding. So this is instance-wise. What we mean by instance-wise is that we always compare two elements in the image at the same time. So the upcoming slides are going to explain this very simply, hopefully. So for example, let's suppose that you're trying to understand what's the relation between object 4, which is this bag, and the laptop, which is labeled as object 3, right? As I said, we're targeting the occlusion and the depth orders. So first, let's initialize two empty graphs, one for the depth and one for the occlusion. we take each element and we put it as a node in those two graphs, and we're gonna fill in the graph between every pair. So we're gonna get all of the edges, which are relations between the nodes, between the instance, one by one. So for example, here we're gonna compare 3 and 1, and so comparing 3 and 4, sorry, and comparing 3 and 4, we can see that 4 is in front of 3, but we can also see that so this is for the depth, but for occlusion, we can also see that the handle of this bag here is actually hiding a little bit this computer here. So what we do is we report this in the graph. So here, this is exactly what we're saying. 3 is in front of 4. So we draw an arrow from 4 to 3. And here we're saying the same. So occlusion is just a fancy name for is hiding, right? Essentially, the question we're asking is like, what object is hiding which other object? So here, for example, we would say 3 is hiding 4. And we would also put an arrow here from 4 to 3. So now we can continue with this simple reasoning for all of the pairs in the image. So here we're computing between the bag and the cat, and so we observe that the bag is in front of the cat. But we observe something a little bit more interesting, which is that for occlusion now we have a case where it's a bit more ambiguous, right? Here the cat is actually in the bag, so the cat is essentially hiding the bag, but the bag is also hiding the cat, right? So we denote this as bidirectional occlusion orders. So here, as you can see, I put it here, 4 is hiding 0 and 0 is hiding 4. And the way we report this in the graph is simply by having this bidirectional arrow here. So as you can see, before we had arrow going in one direction, but now we have arrows going in two directions. Okay, and now we just do this for all of the instance pairs, and that pretty much completes our matrix. So sorry, when I say matrix, actually I mean graph, but graph and adjacency matrices are just the same object, is just the representation which is different. So whenever I use the word matrix, you can think of graph, and whenever I use the word graph, you can think of the word adjacency matrix. Yeah, so now we have our graphs. And yeah, so let's continue on. So like the thing that I want to like now ask is like, all right, so now that we know how the problem is what problem we need to tackle, how do we actually tackle it, right? So our goal is, given all of those nodes, we want to predict all of the relations, all of the edges in both the depth and occlusion graph. So how do we do this? Well, the first line of work that try to tackle this issue are generally called pairwise networks. The name is pretty straightforward. Pairwise because they just take a pair of objects as input, and they give you the output, which is just the edge between those two nodes. So let's see what it means with drawings. It would be easier. So we have this input image here, where once again I labeled all of the objects as 0, 1, 2, 0, 1, 2. And the pairwise networks as input, they take this image and two binary masks. So as you can see here, we have the image, we have the two binary masks, which represent, here they represent 1 and 0, and we feed that into the pairwise network. And what the pairwise network gives you as output is it simply gives you, it tries to answer the question, is 1 occluding 0, and is 0 occluding 1? But it can also, so just using two different linear layers as output, you can also ask the question, is 1 hiding 0 or is 0 hiding 1, right? And essentially, after you do this, here you get that for the mask 1 and the mask 0, and then you get one edge in the occlusion and depth graph here. So then you just repeat this. You just repeat this for all of the pairs of masks in the image, and you finish to construct the graph like that. So here, if you're interested about this line of work, which used to be the very default line of work until 2025, and our proposed networks, you can refer to those references that I put here. These are essentially the three main works that were done to tackle this kind of problem. But okay, that's for one type of model that can solve this problem. But there might be also other ways. For example, what I showed you in the motivation in the first few slides was that we were trying to use a vision language model as the predictor, right? So how do we do this? Well, it's very simple. And now instead of having the masks as input, we just simply have the image. And instead we feed a prompt, right? So the prompt is very easy. It's just simply is 0 hiding 1 and is 0 in front of 1. Of course, we can also flip the prompt, like is 1 hiding 0 and is 1 in front of 0. And that just gives you an edge again. So here you can see that the input format is essentially different, but the output format is still the same. Here you still have to reason at the edge level, right? And when you prompt the VLM once, what you get is just a single edge here in the graph. So once again, you repeat for all of the pairs of instances, and that gives you the full graph. Now, another thing that could be interesting is to ask ourselves, well, these days we have foundation models, right? And foundation models are really good for solving all kind of tests in zero-shot manner. So why don't we use them as well to solve this particular task? And well, yeah, you can definitely do that. So the way you do this is actually you can think of foundation models as something that gives you depth and something that gives you segmentation masks. And if you overlay the segmentation mask on top of the depth of the depth mask, you can essentially get object level depth map, right? And then simply based on the ranking between the values in those instance level depth map, you can rank them, and you can get the depth order prediction for all of the masks in the image. So in practice, this is something that we use as a baseline that we propose. The model that we build is actually in this way. So for those who know grounded Dino, we simply use grounded Dino to get the bounding box of the objects. Then we feed it into SAM, we get the masks. And on the other hand, we just use depth anything here. We get the depth map here. And simply by using this Hadamard product, right, we can get a mask level depth map. And after that, we just simply use a heuristic. Heuristic here is just simply saying we're ranking the mask based on their values, right? So the lower values are the closer to the image, and the higher values are the further to the image, further from the camera. And we just rank this, and that gives us the ranking for the depth order, and we just construct the graph with this. Yep. So this is what I mean here. After you do this, you can simply use the heuristic here. So you have a series of masks, you use heuristics, and then you can compute the full graph like that. One thing to note is that in this model, you just run the inference one. So contrary to the other models, the heuristic is responsible for creating the edges. So you have to run the heuristics multiple times, but the inference cost is only at the foundation model level. The thing is that those foundation models can be quite heavy to run inference on. And if you have consumer hardware or if you're in an embedded device situation, that might be unfeasible. And so now another thing that we could think of is, well, remember the pairwise networks, right? The pairwise networks are actually the one that solve the task the best in terms of performances, and I will show you the benchmark later. But they're pretty annoying because if you remember properly, if I go up a couple of slides ago, the pairwise networks as input, they take those binary masks, right? Which means that you need to have a binary mask input, which is very cumbersome, especially if you don't have annotations before that was made beforehand. So one thing that you could try to do at that time would be like, okay, so how can we do this? Well, we can simply use the raw RGB image, put this into a segmentation network, and that gives you all of the masks that you need. And then on top of that, you add a pairwise network here. So now essentially what we did is we removed the input requirements for those binary masks, but we still have them generated by the segmentation network. So this approach still behaves at the edge level, which means that you're only getting one edge per forward pass. But at the same time, you're sort of like, loosening the input constraint because now it's only just an RGB image. But what we argue is that this is not satisfactory because in all of the previous methods that I showed, there's always some kind of problems, right? For example, for the foundation model, you can only get the depth graph. It's really ambiguous how you get the occlusion. For the pairwise network, you only getting one edge in the graph. You're not getting the full graph at once. For the VLMs, they actually perform pretty poorly, and that's the same thing. You need to infer, even if you take LLaVA, you need 7 billion parameters to just infer one edge, right? And actually, we got ourselves into a very funny situation when we were running the benchmark experiment for that, because when we were trying to benchmark LLaVA, what we observed was that we needed something like 48 hours to run the full inference on the validation set, which is kind of absurd, right? Um, so instead, we were just thinking like, what's the main problem? Why do we have to still run inference at the edge level, right? And that's why we want to propose InstaFormer. InstaFormer, essentially, the idea is to say, let's strip down the problem to what it actually is. We're not trying to predict edges. We're just trying to predict the full adjacency matrix at once, right? That's essentially what we're trying to do. And also strip away the masks, just give us an RGB input, right? So that's essentially the framework that we're behaving on. So if you look at what I mean here, you have an RGB image, you have our InstaFormer network, and the InstaFormer network gives you the full adjacency matrices, which are just simply occlusion and depth graphs, essentially. So in a single forward pass, what we're getting are those full occlusion and depth matrices in a single forward pass from a bare RGB input. And so, yeah, under the hood, how does that operate? Well, we're not outputting those graphs right away, but instead, and that's why I said that when I use the word matrix and graph, you can think of them interchangeably, because we're actually outputting adjacency matrices. And adjacency matrices are just essentially another representation of your graph for the occlusion and for the depth graph. So here, this slide is actually telling you about just a small reminder for adjacency matrices, in case you're not up to date with this. But given this input image with the three labeled instances here, you initialize some occlusion matrices and some depth matrices. And what you see is that you can think of each row and column as representing each instance. So, for example, here you have this teddy bear here. All of the row for this for this instance 0 represents a relation from the teddy bear. So here, for example, let's read it together. We would have, what's the occlusion relation from the teddy bear 0 to the teddy bear 1, and that would be, and the value would be this value here. So here 1 essentially means that there's an occlusion between teddy bear 0 and teddy bear 1. And here you can go also further, and you can say, like, for example, you can read it here for the second here. So you would say like, oh, what's the occlusion value between teddy bear 2 and teddy bear 0? Well, it turns out that teddy bear 2 is not occluding teddy bear 0, right? And here you would have something similar for the depth, right? Where essentially you're gonna ask yourself, well, is teddy bear 0 in front of teddy bear 1? And yeah, the answer here is yes, so we put a 1. And if it's not the case, we put a 0. Here you might notice that the diagonal has -1. Actually, the diagonal can be manually filled because when you think about it, it doesn't really make sense for an object to either occlude itself or being in front or behind itself. So you can always think as the diagonal is just manually filled, right? It's not really we just like remove it anyway. All right, and so the key idea that I want to convey in that slide is that each entry in the matrix represents a compatibility score between objects. And of course, the compatibility score depends on the task that you want to solve. So whether it's going to be occlusion or whether it's going to be depth. But you will see in the way we model the problem in our architecture that if you think of an entry in the adjacency matrix as a compatibility score, a geometrical compatibility score between two masks, that makes a lot of sense. So the main thing that I want to convey is please remember to keep in mind this representation, or each row of the adjacency matrix and each column of the adjacency matrix represents an object, because it's going to help you a lot to understand how the method is designed. So speaking of the method, this is our proposed architecture. I'm not exactly sure how many of you guys are how do you say familiar with the InstaFormer network, which is a segmentation network using transformers. But if you know that, you might recognize that the left part is essentially just InstaFormer. We simply reuse exactly pre-trained InstaFormer without any modification. And the only thing that we're doing is we're leveraging the output of InstaFormer directly in the latent space. So for example, here, we're gonna go quickly over there, but the output of InstaFormers are three tuple of here object queries, masks over there, and per pixel latent representations. So what do the output actually mean? So the masks, well, I mean, I don't really know if there's any explanation to give you on the masks. It's just literally the masks from the input RGB image here. So that's one thing out of the way. The second thing here, those object queries denoted Q, these are a latent representation of the object. Each tensor here can be thought as a latent representation of that object as a convolutional kernel that gets convolutioned, convolved rather, on this high dimensional latent representations here, and that gives the masks, right? So here, essentially, you can think that this blue tensor here is simply a latent representation for one object. And here on the bottom part, well, this is what you get with a typical like segmentation networks. This is just a high dimensional per pixel features, and we're gonna leverage this to compute the orderings. And this part is the geometrical order module. So we're gonna dive into that step by step. So here, the key idea that I want to convey now again is that what we're gonna do in the upcoming slide are simply we're gonna create two sets of the same objects that have complementary representations. And if you remember the other key point that I told you earlier, this might make sense, right? Because remember that each row and each column of the geometrical matrix represents an object, right? So if we have two latent representation of those objects, of those same objects that contain complementary information, then we can simply use the idea of the compatibility score, as I told you before, to aggregate the information using a simple dot product. So that's really the key idea behind the method. So let's go about it step by step. The first thing that we do is we're getting those queries here, and we don't really touch them. We just filter the queries that don't refer to any object, and we just leave them over there. Now on the bottom side, we have a first operation that is happening here. We're taking the latent representation of the per pixel features, and we're essentially dot producting them to the masks that have been generated above. And that gives us per object, per pixel features. So these features are pretty large, and essentially they contain a lot of per pixel geometry of the objects at that location. Manipulating those objects is pretty bulky. So what we're essentially doing is first we're performing attention on each of those elements individually. And then we're 2D pooling that representation to fall back to the same formulation as we have with the object queries here. And now, remember what I told you a couple of minutes earlier? Well, it's almost game over now. Because what we have on one side is we have latent representations of objects that contain information from the transformer of the segmentation network. And on the bottom hand side, what we have is we have the exact same objects that have complementary information, because this information comes from the per pixel decoder representation. So that's why this tensor here is colored in blue, and this tensor here is also colored in blue. This tensor is colored in yellow. This tensor is colored in yellow. And the reason why is because even though they're like yellowness color slightly differs, they still refer to the same object. That's the key point. So now from here, it's pretty straightforward. What we do is we simply concatenate those two representations together. That gives you just essentially a long list of latent object representations, and we forward this into the transformer decoder. This transformer decoder is 8 layers, and after that we chunk back the representations to their original shape. And now, once again, that's the moment where I ask you to remember what I said earlier about the fact that we're going to treat each row and column as latent representations of the objects. Now, you can consider those transform queries as they have interacted with their counterparts from the other set, right? We forward that into simply a single MLP on one side, a single MLP on the other side. And after that, we're doing a dot product between each of these features together. So here, the blue feature is going to be a dot product to the blue feature, to the yellow feature, and to the green feature. And here, the yellow feature is going to be dot producted to the blue feature, yellow feature, green feature. And after that, we forward that into a test-specific MLP. So here you can see there are 2 MLPs. One MLP is in charge of outputting the occlusion adjacency matrix, while the other MLP is in charge of outputting the depth adjacency matrix. And yeah, that's pretty much it. We just naturally fall back to this adjacency matrix representation by using this clever dot product here. The way we supervise this is very simple. We use binary cross entropy losses, and we just supervise each of the entry in the matrix to match their ground truth. If you want more details about that, I just refer you guys to the paper. So here I want to dive a little bit more into this last part of the computation, which is essentially the most important part, because that's where the sort of like clever idea occurs, right? The fact of treating each entry in the matrix as a compatibility score. So here, for example, you have you have the first tensor, and as I said earlier, you have the first tensor on the left, the second set of tensor on the right. And what happens at the dot product here is essentially what I was trying to encapsulate in the figure on the right. So here, as you can see, the masks here, they're just like your, let's say, representation as humans, right? This represents a mask, but what that mask is actually is simply a tensor like that. It's a high dimensional tensor. And now if you're doing a dot product between this tensor and this tensor, as I show here, for example, this tensor and this tensor here, you're simply doing a dot product. And that collapses the latent dimension into a single scalar. And that single scalar, so you can think of this as some kind of similarity, right? This is the similarity operation that I was talking about before. And this single scalar is actually the prediction of the network. Yeah, and so if you understood this, this is essentially the crux of the method. And this is, yeah, if you understood that, you essentially understood how we reformulated the problem and how we get away with a single forward pass to generate those final adjacency matrices. So for training, we use the InstaOrder dataset. You can refer to the paper if you want more information, but essentially that dataset gives you those graphs, exactly those graphs. So depth and occlusion, and this is a prior work from our lab. So yeah, shout out to Hyunmin who led the project. Yeah, so this dataset is the largest dataset available for those kind of occlusion and depth orders by far. And it's human annotated, so which means that the quality of the ground truth that you get is actually pretty solid. So for measuring the accuracy of our networks, for occlusion order, we use the very famous recall precision and F1 score. So I'm not gonna go over those because I guess most of you guys already know it. That's essentially just higher the better. For the upcoming benchmark presentation, we're mostly focused on the F1 score because this is the harmonic mean between the precision and the recall scores, which means that this is sort of like the value that you want to keep track of to really measure the quality of the prediction of the network. For depth order, we use a metric which is called the weighted human disagreement rate. And the reason we use this metric is because the task of depth order is actually pretty tricky for humans. There are situations where, given a 2D image, it's pretty hard to tell which annotation, which element is in front of the other, right? In the 3D space, we do it quite well, but when the 3D is sort of like collapsed on a 2D representation, it might be a little bit tricky, and even humans are prompt to many hallucinations and illusions that can happen in when evaluating depth orderings in the physical world. So instead, we use this proposed metric from previous work, which is the weighted human disagreement rate, and let's simply dissect it together. So for each annotation of the depth matrix, so for each entry in the depth matrix, either annotated 1 or 0, we also keep track of, so you have a pool of annotators. You have, let's say, 3 annotators, and we're asking the 3 annotators to annotate the same relation. So one guy annotates the relation, the other annotates the same, the other annotates the same, and then we're asking, are the guys agreeing? And it turns out that in some cases they're not agreeing. When they're not agreeing, we consider that annotation to be hard, right? So we give it a weight. So if they agree the first time, the weight is simply 1. But if it takes them like whatever, let's say 4 attempts to agree on the annotation, then we're gonna give a larger weight here, right? This is just simply the accuracy. So this is simply, is the prediction of the model matching the ground truth? And then this accuracy is weighted by the difficulty score, right? And here, this is the sum of all of the difficulties of all of the entry in the sample. So essentially, you can think of it as some kind of weighted accuracy, where when the annotation is harder, it's gonna account more towards the final prediction, final evaluation metric. So that's what WHDR is. So yeah, just think about it as some kind of weighted accuracy based on the difficulty of the annotation. So here, in the upcoming slides, I will present the results for the main benchmark of our work. We have led multiple ablation studies and other interesting experiments, but given the let's say I want to keep the presentation sort of like high level, and also want to focus more on like this singular benchmark. So if you're interested about that, I refer you to the paper once again. All right, so yeah, let's start. For this benchmark, I will mostly focus on the F1 and WHDR all accuracies or metrics rather, because they're the more let's say the more representative of the quality of the prediction of the network. So first, let's evaluate VLMs. So for VLMs, as you can see here, we have 2 lines. We have LLaVA and LLaVA with this kind of like an asterisk here. The first line is LLaVA zero shot. So this is the vision language model. We just evaluate on the InstaOrder dataset without any training. We just freeze the network. And what you observe is that the F1 is extremely low. It's 34. And the WHDR, so a WHDR is lower the better. Here it's 39. Actually, it's the largest out of all of the benchmark method. Even methods that are non-parametric are actually performing better than this. So LLaVA is actually performing almost worse than random, which seems to say that there's some kind of imbalance during the training of the network, but I'm not gonna deal too much about that. So the second thing that we did is we just fine-tuned LLaVA, right? So here we fine-tune LLaVA, and what we can see is that we have a substantial improvement in the F1. Now we're getting to 60.4, and WHDR is also dramatically dropping. But those values are still behind values that you could expect from specialized pairwise networks. So let's say LLaVA is the worst students out of all of the students in the class that are trying to perform this task. LLaVA is definitely the one that's at the back of the class and just like scrolling on TikTok while doing the evaluation. All right. And the second type of things that we evaluate are the foundation models. So the foundation model, I show you the pipeline again before. We're using grounded sum and we're using depth anything. And so for this particular architecture, there's no straightforward way of obtaining the occlusion order prediction. So we simply evaluate on the depth order prediction. And when we do this, we observe that the results are like, 20. So we have different types of heuristics. I once again, I referred you to the paper if you're interested in the heuristics that we use, but we developed 3 heuristics, and you can see that median is the best heuristic that we have, and median is about 22, which is still behind the specialized pairwise networks. So now onto the main baselines. So here I highlight the most competitive pairwise networks, InstaOrder-OD, InstaOrder-OD, and InstaOrder-OD. O means it only performs occlusion, D it means it only performs depth, and OD means it performs joint occlusion and depth prediction. Here you can see that now the results that we have are much more competitive. F1 now is above 80, and actually InstaOrder-OD shows a very strong 81.86 F1 score, while the WHDR breaks below the bar of the 20 score, right? So now we have 17.5 and 15.9. So at the time of making our work, making InstaFormer, this baseline was actually the strongest baseline. And remember what I told you, this baseline is very cumbersome to use. So what we propose is we propose a model which is called mass-to-order, which uses a segmentation network. And on top of that, adds the pairwise networks. And when we do that, what we observe is that the results are actually not that good in comparison to the pre-trained, to the trained InstaOrder-net pairwise networks. And the reason for that is because when the segmentation network creates the masks, it's really hard for the pairwise network to adapt to the lower quality of the segmentation masks. So we have 2 experiments: the experiment with simply O and the experiment with this asterisk again. So for occlusion, for depth, and for occlusion and depth. And you can see that when we have the asterisk, it means we're retraining the full pairwise network on top of the segmentation backbone. And even when we retrain the network from 0, what we see is that we only get like 79.1 F1, whereas the baseline was at 80.65, right? So there's still a very noticeable drop of performances, even though we're really trying to push the performances as much as we can by retraining on top. And the same goes here for the depth order prediction. It's lower than the predictions that we could have with the pairwise networks. And so now finally on to the comparison with our approach, which is InstaFormer. Well, now you can see that InstaFormer beats the previous state of the art, and it beats it while behaving in a more challenging setting. Because remember, the pairwise network, they only have the they have the RGB input plus the segmentation mask as input, and they only give you an edge in the graph. Whereas now we simply have the RGB input and we get the full graph prediction at once. So even though we're behaving in a way more challenging setting, you can see that our network substantially outperformed, especially for the depth order, substantially outperformed the previous base sets. But on top of that, this comes with some very nice property because we're predicting the full graph at once. We conducted memory inference runtime comparison. And you can see that if you look at InstaOrder-net, which is the pairwise baseline, the best pairwise baseline available, you can see that if you increase as you increase the number of instances, its inference speeds get slower and slower, right? Exponentially slower and slower. And the reason is very simple. Think about what a graph is. A graph is the set of nodes, and each node can be connected to all of the other nodes, right? Which means that as soon as you add one other node in the graph, the complexity increased by a quadratic factor, right? So this is something that's very obvious to see, right? If you add more graphs and you do inference using the pairwise networks, then you see this exponential curve appearing. But on the other hand, our network appears constant in terms of inference cost with respect to any number of instances. One thing that you could do now is there's a, let's say, smart way of running the pairwise models in a batchified manner. I'm going to skip the details, but if you use the pairwise networks in a batchified setting, you can see that the inference speed now becomes much better. But on the other hand, this red curve here, you can see that the memory in gigabyte becomes exponentially increasing now. And to the point where you cannot perform inference above 20 instances. Here we get CUDA out of memory errors. As you can see, we were already more than 40 gigabytes of memory used, whereas us appears linear with respect to the number of instances. And on top of that, our approach, so not only do we achieve a better runtime memory trade-off, our approach scales very, very nicely. In the evaluation set of InstaOrder, what we find is that we can predict up to 63 instances in a single sample. And I think that this is only limited by the number of images that's available in the annotations. But I'm pretty confident that we can go into like one order of magnitude above and maybe predict up to 200 instances up to the full amount of object queries that are available. So I'll quickly wrap up with some validation and out of distribution results. So here, for example, you can see that in this challenging setting where the car is, so the funny thing is that the car here is partially segmented, right, by the segmentation backbone. This part is actually referring to the same object, but if you look at the depth order, the car is still accurately located in the depth graph, right? So car 4 is in front of car 2, car 1, and car 3. Car 3, car 2, car 1. So actually, yeah, that's right, because it's on the road, right? So even in those kind of like very peculiar, challenging setting, our network still managed to perform some very good predictions. For occlusion here, you can see that nothing is really occluding each other. You could argue that this pole is actually occluding the car, but actually the annotation for stop in the dataset only covered this part. So technically, our network is aligning with the dataset. Here, this is a very simple image. Yeah, I'm probably gonna skip over this one because it's quite simple. It's just to show you how we can predict very accurately very simple graphs. And here, on the other hand, I'm not gonna ask you to verify everything because you can see how those kind of like depth graph, when you try to visualize them as graphs, right? They can pretty quickly become very hard to grasp. The main reason why I put this example here is just to show you that even when we have a lot of instances in the image, we can still predict something that makes sense and something that we can still get an output in a single for our test. Now, the next two images that I'm going to show you are out of distribution results. So these results are very, I think, interesting, and that's the one that I think are worth looking for. The input image is, as you can see here, those K-pop idols. And we have barely any clue, right, as to what's the geometry is because it's only silhouettes. But we can see that, so here, if you look at the occlusion in that graph, what I tried to do for that figure is I tried to arrange the nodes in the graph as some kind of bird's eye view of what the network is inferring, of the order that the network is inferring. So here, for example, you can see person 5, I tried to put it at the bottom. So person 5 is actually the person that the network thinks is the closest, and then followed by person 3, person 4, person 1, person 7, person 6, and person 2. And it's very funny because the first time I looked at this image, I thought that the K-pop idol at the middle was actually the one the closest to us. But after seeing the prediction of my network, I realized, wait, the network is actually right. It's making a circle around person 4, right? Which was very interesting. It was a good reality check that actually humans are not that good at determining those kind of depth order in the scenes, but the network was actually surprisingly very good at that. And finally here, well, you might not know what to look at first, and the reason is because this is also an outer distribution result. What I want you to pay attention here is, I don't know if you can see it on Zoom, but there is a ball here, a very tiny table tennis ball, gesture. And if you look at the occlusion graph, that ball must be isolated because it's not occluding any of the players and of the rackets. But if you look at the depth graph, you can see that this ball is accurately placed in front of bracket 3, person 1 in bracket 4. If you look at the arrows here, there's an arrow from ball to person 1, ball to bracket 1, ball to person 3, and ball to bracket 3. So even in the case where we have very tiny objects, we can still get some very accurate depth and occlusion orders thanks to our network. So I will conclude very quickly with this kind of let's say expanding questioning, which is, can we use this instance-wise understanding to improve over other models? What I showed was that we can use them to improve the vision language models in a zero-shot manner, but I think that further work should be done to uh, incorporate those kind of instance-wise understanding mechanism directly during training when we're training, let's say, dyno models or SAM models. And the reason why this is needed is because simple description of the scene is not enough anymore. We need to go to better understanding of the scenes, which means that we need to understand the relations between objects. We do not need to be stuck at simply generating a mask for one object without putting it in relation or in context to the other masks. We need to draw those kind of relations to go further in the field of scene understanding. And overall, I think to achieve what some would call AGI, but at least a generalized, a deeper and more fundamental vision algorithms. So yeah, thank you very much for listening to my hopefully, not that boring talk, I hope. And if you guys have any question, I would be very happy to answer them. So I think I'm in time, right? Yeah. Thank you very much.
So I will ask our first question. So how often do predicted occlusion depth graphs violate consistency? Like example, like occlusion cycles, right? Depth, anti-symmetry. And do you apply any post-processing or constraints to enforce validity?
Okay, so that's a very good question. Actually, to answer the second part of the question first, our network is trained without any restriction. We just simply use the annotations from the dataset, but we do not regularize it in any way. And second, so that indirectly answers the first question as well. And what I want to emphasize as well here in the benchmark is that if you look at the results here, the depth order prediction um, score is notably lower than for the previous pairwise networks. And we haven't shown it explicitly with an experiment, but I assume that this is a very clever question, because I assume that this is due to the intrinsic nature of the depth order graph. So the depth order graph is always symmetric, because when an object is in front of another one, that other object cannot be in front of the same object anymore, right? And we believe that even without any regularization or a constraint on how we want to have the output, the network implicitly learns this kind of geometry itself. So that would be something that would be very interesting to highlight with a separate experiments, but we haven't done it in the papers. So that would be a good follow up study.
Makes sense. Um, do you guys have any other questions from our research members? Um, if not, I will ask one more question. So, have you evaluated on other data sets with occlusion depth annotations? So, like example will be like COCO and KINS, right? If not, like what pairs exist and do you like anticipate similar gains?
That's a very good question. So, actually, the reason we tackled the InstaOrder dataset first was because of the scale of the annotation. One thing that I found out was that it's very easy to train this network on InstaOrder. There's no on the InstaOrder dataset. There are absolutely no instabilities. When you run multiple runs, you get very similar, like low variance. But as soon as you fall back to the COCOA and KINS dataset, the dataset size is very, very low, right? In comparison to InstaOrder, we have millions of annotations, but KINS and COCOA were limited to like 1,000 scale annotation. And the problem is a very fundamental problem in computer vision, but also just in general machine learning, is that training transformer in low data regime is actually pretty tough. And so what I observed was that as soon as you don't have enough quantity of annotations, um, our approach tends to have some limitations. So that's why I was also mentioning in the end slide here that we probably need to integrate some kind of like self-supervised, setting into this kind of methods in order to make them more data efficient, and that could be, I think, a very interesting also future direction. So definitely our approach has some limitation in that regard. Yes.